let's start, as we often do, with the problem. So this is probably one of the most beautiful phrases to a student who's taking calculus. Rewrite, but do not evaluate. I'll tell you, nothing makes a calculus student more happy than seeing the phrase, do not evaluate. So we're just working on practicing doing our change of variables, but we're not going to actually finish the integration part. So we have this integral, goes from 0 to square root of a half, and then y squared to 1 minus y squared of 8xy plus 8y cubed, all over 1 plus the quantity x minus, 1 plus the quantity of x minus y squared cubed. And that's integrated dx dy. And we're going to use the change of variables, u equals x minus y squared, and v equals x plus y squared. I do know people are nervous. How will I figure out what the right change of variables is? And I will tell you that for the problems that you're going to encounter, that you have to do, the answer is you look for this phrase, u equals and v equals. We will give it to you. So you're not going to have to guess. So there's enough to do without having to guess what it is. And it's not easy to guess what your substitution should be. And this really is essentially multivariable substitution is how you should think of it. And even when you're doing Calc 1 stuff, it can be tricky to think about what the substitutions are. So just take those as given. And now what we want to focus on is the next stage. So the next stage says I have 3 parts to my integral that I have to take care of. How do I break things up, which is the Jacobian part, the function, and the bounds. And I like to go in that order, because it's actually useful to know the Jacobian before you try to tackle the function, because it will influence what is the actual function. So let's talk about that. So what we're going to do is we're going to start with u equals and v equals. And we're going to do the following. We're going to set up a little 2 by 2 matrix and take the determinant. So it's u sub x, u sub y, v sub x, v sub y. And like I said, this matrix is very, very forgiving. So if you write, say, u sub x and u sub y in the first row, and v sub x, v sub y in the second row, you'll still get the same thing, because it's very forgiving. So don't fret too much about getting it exactly right. Just be consistent. So for example, here I have u's and v's in the columns, and I have x's and y's in the rows. And as long as you have some consistency, it'll work out. So we're going to take the determinant of this 2 by 2, and then if we need, we'll take the absolute value. So I'm going to just put that in as a reminder that whatever comes out, I'm going to take the absolute value. Okay, so let's take these partial derivatives. What is u sub x? It's 1. Let's come over here. What is v sub x? 1. Oh, good. What is u sub y? Negative 2y. What is v sub y? 2y. And we take this determinant and make sure whatever we get the absolute value. So it's going to be 2y. Then we're going to subtract negative 2y, which makes another plus 2y. And we say, oh, okay, well, y is certainly positive in our range, and therefore our answer is 4y. Now the question is, what is this telling us? So here's what's going on. We have the following fact. We have that du dv is, in general, what happens when you take this Jacobian, u sub x, v sub x, u sub y, v sub y, times dx dy. Conversely, you can say that dx dy is, you take the Jacobian, but now what you do is you say, let me solve for x and y in terms of u and v. Now, of course, to do that, you actually have to do some work to figure out what is x in terms of u and v, what is y in terms of u and v, du dv. So I prefer this method, the one that we're doing right now, because it doesn't require me to solve for x and y, which saves us a step. And I always like to avoid extra work. So what we've concluded, because of this computation here, is that we have that du dv is equal to 4y dx dy. So that's how we're going to be affected by our rewriting of things. So now we come to the next stage, which just says, let's look at our function. Now we're going to be a little bit more careful here. So what do I mean by that is we have this expression here, and I'm going to say, okay, I want to pull out a 4y dx dy on the end, because that 4y dx dy will translate to du dv. So I say, okay, I see there's an 8y and an 8y cubed. Those are perfect candidates to pull a 4 out. Well, really to pull a 4y out. So if I pull the 4y out and put that on the end, 4y dx dy, then what's left? Well, downstairs I didn't do anything, so it's still the same as before. 1 plus x minus y squared quantity cubed. Upstairs, well, I pulled out a 4y, so here I see a 2x, and here I pull out a 4y, so that would be a 2y squared. So I haven't I haven't changed the function in terms of u and v, but what I'm doing is I'm trying to isolate what's the part that I need to change in terms of u and v. Again, the 4y, this part, we're happy with this part. We're not going to do anything. This part, the 2x plus 2y squared over 1 plus x minus y squared cubed, that's the part we're going to rewrite in terms of u and v. So we look at this and say, all right, we want to write everything here in terms of u and v. There can't be a single x or a single y left. Everything has to be rewritten in terms of u and v. So let's start with the denominator. What can we do to rewrite this in terms of just u's and v's? So it's u, right? So it becomes 1 plus u cubed. Now how about upstairs? Yeah, 2v. You might say, 2v or not 2v? No, it's 2v. Because you could pull a 2 out, then you get times x plus y squared, and x plus y squared is v. So that says this is what your function will become. So we've done here's what's become, this part here is going to become our du dv, or possibly our dv du. It just depends on what happens with the bounds. We'll figure that out in a second. And so we have our function, we have our du dv, life is good. What's our last thing to do? Yeah, we change the bounds. And when we say change the bounds, what we really mean is let's describe our region. So we have to start with our current region. We know our current region that y goes from 0 to square root of a half. And that x goes from y squared to 1 minus y squared. Now, if you were to sketch this, and we will sketch this, what do we see? Well, we see this curve x equals y squared. What does x equal y squared look like? It's a sideways parabola. It opens to the right. So there is our x equal y squared. Now, what does x equal 1 minus y squared look like? Yeah, so it opens to the left, and then there's been a shift. Now, which way did we shift it? We shifted it to the right. So that the vertex here is at 1. Okay, so that is our other curve. X equals 1 minus y squared. Now we say, well, where does y go from? Well, we start at 0, and y equals 0. That's pretty easy to spot. It's right there. And then we go up until we hit a certain point, square root of a half. Well, we suspect it might be this intersection point. How could we check if it's that intersection point? Well, the answer is we'll figure out what is that intersection point. That would be when y squared equals 1 minus y squared. 2y squared equals 1. Or y squared equals a half. So that is, in fact, where it goes to. So that's our region. So once you have identified what your region is, the next stage is to say, okay, let's look at the bounding curves. What curves bound this region? So this one, if you look at it, it has 3 pieces. So let's talk about our 3 parts. What's the one down here at the bottom? Y equals 0. So these are our bounding curves. The first one we said is y equals 0. All right, how about the one on the left? Yeah, it's x equals y squared, right. How about this one on the right? Right, it's x equals 1 minus y squared. Now, what you want to do is you want to take these bounding curves and you want to say, well, what are these curves becoming in terms of u and v? So let's maybe start with this last one. What can I do to make it look like something involving u and v? Yeah, we could add y squared. So that would become x plus y squared equals 1. What does that become? V equals 1. How about the middle one? What can we do? Subtract y squared. What does that become? U equals 0. Okay, y equals 0. Now you say, well, that's not so clear. But let's take a look at it for just a second. Say, okay, if I don't know what to do, what we do is we just plug y equals 0 into both expressions and see what happens. So when we plug in y equals 0 into the first expression, what do we get? U equals x. If we plug y equals 0 into the second expression, what do we get? V equals x. So we know that when y equals 0, it has to be the case that u is x and that v is x. Well, if u is x and v is x, what's true about u and v? They equal each other. And therefore, this last curve is u equals v. So those are my 3 curves which will bound my region when I translate this into the uv plane. So we sketch those 3 curves. So if we say u, v equals 1, something like that. U equals 0 is over here. It's the v-axis. And u equals v is this line. And so what we're looking for is what's the region that's containing these 3 curves, or bounded by these 3 curves, and it's this triangle. So what happens is that when we change the substitution, this triangle with somewhat bent edges becomes a new triangle. A little bit easier to describe. And that's one of our goals. We're doing a change to make things easier. We don't do a change to make things harder. That's the wrong spirit of calculus. All right, so now we're ready to do our integral. Integral, our function, 2v over 1 plus u cubed. Now, the question, do you want to do du dv or dv du? We don't actually have to do the computation, so we can do either one. Which one seems easier to describe? Now, suppose we did have to do the computation. Which one would we want to do? You probably would want to do dv du. Because why? Look at the integral. What's easier to integrate, with respect to v or with respect to u? You definitely want to integrate that with respect to v, because I can it's v squared. 1 plus u cubed on the downstairs, I was told that was possible, but I don't know. Okay, so let's talk about where do things go from. Where does u go from? 0 to 1. And then, for a particular value of v, for a particular value of u, where will v run between? V to 1. And that's it. Because we only had to get to the setup. Rewrite it. We don't have to evaluate it. But you can see there's a process here. Find your Jacobian. Figure out, okay, what happens? How do I get my du dv? Pull out what you need. Then you say, okay, how does that become my new function? All right, now figure out what your new bounds are. And you can use the function sometimes to help dictate what's the order of integration, because that can give you some insight as to which way to do it. All right, so that's good. Woohoo! So we're going to be transitioning to a new part of the course. So it might be helpful to remember what we've done so far. So far we've been primarily concerned with what we might call scalar-valued functions. Now these are the kinds of functions where you input a number and out comes another number. Now it might be multiple numbers. So for instance, when we talk about surfaces, z equals f of x comma y. So you put in two pairs of numbers, out comes a single value. But there's another type of function which is going to be very important, which are the vector-valued functions. And these are the functions where the output is a single vector. Now we've already seen examples of vector-valued functions before. So for example, when we talked about motion, we said our input was time, and our output was a vector that indicated somewhat of a location, x of t, y of t, z of t. Now that's not the only kind of vector-valued function we've seen. Another important type of vector-valued function we've seen are one where we put in a pair of numbers, and out comes a vector, which is the gradient. So in the gradient, we put in a location, out comes a vector, and that vector gives us information about what the function is doing. So we're really going to be looking into sort of this type of thing, vector-valued functions. So to understand what a vector-valued function does, it might be useful to sort of say, how do you describe these things? And here we say, well, what's the output? See, previously, when we dealt with scalar-valued functions, it was pretty simple. If you think about, for example, y equals f of x, well, you say, here's my input, here's my output, it's a single point. And when you go up to 3 dimensions, of course, here's your input in the xy plane, there's your output is a single point. No big surprises. But now, when we transition to vectors, our outputs are vectors. So how are we going to draw these? What does it look like, and how do we understand it? So we're going to think about the output. We can call these sometimes vector fields. And what we do is we're going to represent our output as a series of vectors. So we can't draw every possible vector. The problem becomes when we try to draw every possible vector, our picture is just far too dense and we can't make sense of anything. So instead, what tends to happen is we tend to sample a couple of vectors, and we use the vectors. Remember, they need to be having a distance, or a magnitude, if you will, and a direction. So sometimes you might see the direction, well, it's always an arrow, and the magnitude is either longer or shorter, or thinner or thicker. It just depends on the applications. So let's look at a couple of these. So here's an example. Suppose I look at my vector-valued function, capital F of xy, is x comma y. So what that says is we come up and we pick a point. So for instance, we might pick a point here. That's an easy point to sort of identify the behavior, because where am I? I'm on the positive x-axis, so the vector from there points in the positive x direction. So if I'm on the axis, I move further up. Or I might pick a point, say, up here. Well, there's a little change in x, but a bigger change in y, and I'm moving in that way. And I do that for many, many points, and I get this shape. Now you might want to say, well, how do I interpret this thing? Now you could interpret it in many different ways. Now one of the ways you might see these things showing up are things like flow. So flow is going to be a really big idea going forward. So it might have like airflow or fluid flow, or you could even go to something like electrical flow. And in those cases, we oftentimes, you might see weather maps where they have a weather indicating how is the air moving. And then they'll have something that looks like this, because air motion is a vector field, because air at every point, you have a direction and a magnitude that it's corresponding to. Now you might say, is there another way to think about what's going on? Well, we could say, what if I were trying to make this the gradient of something? Now, not everything is the gradient of something. We're going to talk more about that in just a moment. But it turns out that you can do the following, that for this particular one, what we see is that xy turns out to be the gradient of 1/2 x squared plus 1/2 y squared. All right. And what is this shape? 1/2 x squared plus 1/2 y squared. Well, that's the bowl. And now, if you think about what the gradient does, the gradient says you should point in the direction of greatest increase. Well, if I'm on the bowl, where's the direction of greatest increase? The answer is I should point away from the center. So you see, that's what's happening over here. I'm pointing away from the centers. So I'm going up, up, up. So that helps us understand things. And so, okay, now this vector valued function is very different. X times y, x plus y. It turns out, we don't have the tools to do this yet, it turns out it's not the gradient of something, so it's not so clear what's happening here. But you can see there's some very definitely different behaviors. Whereas over here we're always moving out from the origin. Well, sometimes we're moving out to the origin, but sometimes it looks like we're moving towards the origin. Sometimes it looks like we're moving somehow perpendicular to where we should be. And it just varies. Very different behavior. Here's a couple more. Say capital F of xy is yx. Now, this happens to be, again, it's not always so clear, this also is one that's the gradient of something. So y comma x is the gradient of the vector field, gradient of the function xy. You can check it. Take the derivative with respect to x, you get y. Take the derivative with respect to y, you get x. And so, what's happening? Well, it turns out that this function, yx, what shape it forms is a saddle. So you have this saddle shape that's getting formed here. Say, okay. So what you can see is that in some directions, remember that we always point in the direction of greatest increase. So you'll see how we're pointing towards the center in this direction. Well, that's coming up along that part of the saddle. So in that part of the saddle, we're moving up. So we should move along in that direction of greatest increase. Then over here, it says, no, don't go towards the origin, go away from the origin. That's that part of the saddle. What if you're somewhere else? Well, if you're somewhere else, you do a different thing. So, for instance, maybe we come along here, and you can almost follow the arrows along. And they're telling you you should follow that along. Now, how does that translate? Well, what it translates into is you're coming up from above, and then you're following up along there. So there's a kind of an interesting topic. There's something called gradient descent, wherein you follow the arrows, and the arrows give you information. Now, that's not what we're going to be talking about now, but there are, of course, nice connections. And here's one more, vector field. Of course, there's infinitely many. We can make all sorts of strange and beautiful and unusual functions. But depending upon what we get, we'll get different behaviors. You might notice in these two here, you actually have sort of this center point where the vector field is almost zero. Well, that's okay. That's fine. Now, generally speaking, we're not going to ask you to draw too many vector fields because it's a little bit challenging to do those. But there's a few that we can get a handle on. So let's start with a nice one. So one type of a vector valued function is force. And so, since we have vector fields, we have force fields. And so we can talk about the force fields. So let's talk about gravity. So the claim is that the following function, capital F of xy, negative k times xi plus yj divided by x squared plus y squared to the 3/2. The claim is that this is modeling our gravity. Now, what does that mean? Well, the way we tend to think about gravity is the following. So you might imagine that you have a very heavy object at your center. So this can be a very heavy object, like a planet or a sun, or if you want to go super heavy, a black hole. So you have this very heavy object at your center, and what happens is it's drawn towards the center. So all our other objects in space are pulled towards this point. So how do we do that? Well, the claim is this function models gravity. So how can we see that? Well, one way to write this is kind of an interesting way to do this, is you have minus k over x squared plus y squared to the 3/2 x comma y. And now I'm going to do two things. I'm going to put the minus inside here. The only thing I've done right now is just change my notation. Instead of xi and yj, xy. I'm going to put the minus inside. Then I'm going to break this x squared plus y squared up. So this would be k over x squared plus y squared to the 1/2 squared. And then I'm going to have a minus x minus y over the square root of x squared plus y squared. Now, you can look at this and say, okay, yeah, sure, what you've done is the same as what you've just had, but why have you done it? So if you come out here and you say, well, let's pick a point. So here's a point x comma y. Now, every vector has two aspects to it, and those two aspects are the direction and the magnitude. So this part, this second part here, this is the direction part of it. And the direction says what? Well, suppose I'm at a point x comma y, and I go to minus x minus y. Well, minus x in the x direction, minus y in the y direction, says that right now we're pointing towards the center. All right, so that tells us we point towards the center. Now we divide by root x squared plus y squared. That tells us that we're going to make this part the unit vector. So right now I have the unit vector pointing towards the center. That's what this second part does. But remember, there's another part to vectors, and that is the magnitude of a vector. So that's coming from this first part here. So this is our magnitude. Now, if we're gravity, what's the magnitude become? Well, you'll often hear the following. Proportional, that means the k. So whenever you hear the word something is proportional, then the other thing you'll see is the reciprocal of the square of the distance. Now, how do we translate that statement? The reciprocal means 1 over, and the square of the distance says you take your distance function and you square it. Well, that's your distance function in there. X squared plus y squared is 1/2. We squared it, and then it's on the bottom, so it's a reciprocal. So that's why this is the gravity. It's proportional to the reciprocal of the square of the distance. That's our magnitude. So that means that if I'm far out, it's a very short arrow. So things which are far away have a very short pull towards the center. Now, how do I get a stronger pull? Well, the answer is, of course, you get very close. So the closer you get, the stronger the pull becomes. So if I move in, my arrows get longer. And you might say, well, what happens if you move in really close? Well, if you move in really close, your arrow gets very long. It could even go past the center. Now, it would actually cross over the center, but I'm just putting it here. Now, why would it go past? Well, it's just remember, you're starting here, it might be very strong. And if you got really close here, it would be super, super strong pull. And so there we go. It's pulling us towards the center, towards the center. That's what it's doing. That's gravity. Now, it's a little bit hard to see this picture. Of course, it's really hard to see any picture with vector fields just because there's a lot of arrows. Now, when we have that our function is the gradient of some function, we mentioned a couple of the vector fields on the previous page where that was true, we say that the function f is conservative and that little f is a potential function. But here's how you should be thinking about it. You should think of this symbol here. Now this is not the gradient symbol. This is the del symbol, sometimes called nabla. You should think of that as acting as the derivative. So what we have in some sense is like saying, oh, I have some function little f where when I take a derivative, I get capital F. So in some sense, capital F is the derivative of little f, or you can really think of saying that little f is like an antiderivative of capital F. So that's one way to think of it. So the conservative functions are the ones which have, in some sense, an antiderivative. Most functions are not conservative. And that statement may either not surprise you, or may say like, whoa. Now, you might not surprise you because it's like, well, yeah, because it's hard to satisfy certain conditions. The whoa comes from saying, hey, in single variable calculus, all the functions that we dealt with, which were reasonable and nice, for example, continuous functions, they always had antiderivatives. And so there's something different here going on. So when we add this extra layer, not everything works. Well, it can be either good or bad, depending on the situation. Hopefully it'll be good. Now, let's find the vector field, which corresponds to the potential function for f of xy equals k times x squared plus y squared to the negative 1/2 power. Now, we can always find a vector field for any function. So no matter what function I start out with, I'll produce a vector field. And the way I do it is I do the gradient. So the gradient of f is equal to, I take the vector valued function, in this case there'll be two entries, partial f, partial x, partial f, partial y. In the first entry, what do we get? Well, we'll get k negative 1/2 x squared plus y squared to negative 3/2, and now times by the derivative of the inside, which is 2x. But we'll get the same thing when we take the derivative with respect to y. The only difference is that now the derivative of the inside is 2y. Now at this point, the 1/2 and the 2's cancel, which is great. What else can we do? Well, let's pull out what they have in common. There's a negative, so I'll pull that out. There's a k, pull that out. There's an x squared plus y squared to negative 3/2. So I'll go ahead and put that on the outside, x squared plus y squared to the 3/2. And I'll put it downstairs because it's the negative 3/2. All right, what haven't I pulled out? Well, what I haven't pulled out is x from the first entry, y from the second entry, x comma y. Now, we look at them and say, does that look familiar? Does it look like anything that we've seen before? It is. It's gravity. Gravity. So that tells us that gravity, it's one of these nice things. See, gravity is conservative. That's our takeaway message. Gravity is a conservative function. And you're probably thinking, wow, I always thought gravity was more liberal. It applied to everybody. Everybody falls and breaks a bone sooner or later. Must be liberal. No, it's conservative. Conservative. It works in beautiful, beautiful ways. All right. So where are we heading? Well, we want to get to the point of exploring these vector valued functions, and in particular doing calculus. And the way we're going to get there is to talk about what's our notion of derivative. And so let's remind ourselves that when we're thinking about derivatives, we're really thinking about something special called an operator. Now, an operator says, I take a machine where I put a function into my machine, and out comes a function. So in some sense, it's like a function for functions. Now, we've seen operators all the time because derivatives, that idea of taking derivatives, That's an operator. Because I start with a function, I take a derivative, I get a new function out. And the question, of course, is what do we learn from that new function? Well, for now, let's just say, let's figure out what that new function should be. So in our case, we're saying, well, we're working with vector-valued functions. So what operator do we use? And the answer is we're going to use the del operator. So that's, again, del is this upside-down triangle. So it depends on how many dimensions you have. If you're dealing with two-dimensional objects, del will consist of partial x, partial y. If it's 3 dimensions, del is partial x, partial y, partial z. So del is an operator that works with vectors. So in some sense, it's a vector type of operator. So we start thinking to ourselves, okay, let's think about things that we can do with vectors. And in particular, what we're going to do is build up 3 different operators built on different operations that correspond with vectors, and in particular, vector products. So there's 3 different types of vector products. They are scalar, dot, and cross. So we're going to go through and talk about all those 3 vector products, and then we'll be able to talk about the different types of operators that happen. So the first one is the one that we already are familiar with, which is the scalar product. So the scalar product, sometimes called the gradient of f, which we have the notation del f, it takes a scalar valued function and produces a vector valued function. Now this is the one we're most familiar with because we've been working with it for a while now, so it should hopefully have the fewest surprises. In other words, we've seen it before, and of course, we'll probably see it again. So if I take a function, say function x of y equals x squared y plus e to the x sine of y, that's an example, then del f, gradient of f, is partial f partial x partial f partial y, which is 2xy plus e to the x sine y, took the derivative with respect to x, comma, x squared plus e to the x cosine y, take the derivative with respect to y. So, there we go. There we go. Good. Now, you might be wondering, wait a second, why are you calling this a scalar product? Where's the scaling coming from? Well, here's the idea of the scalar product. See, when we think about del f, the scalar means what? Well, del is the vector. Partial x, comma, partial y. And now, f. So here, f is acting like our number that we're scaling our vector by. So that's sort of the intuition about why we call it a scalar product. Number, vector. And what we do is when we're doing a scalar product, we just distribute through. So that's how we end up with our partial f, partial x, and our partial f, partial y. So scalar product, it works with vectors, functions with any number of inputs. 2 inputs, 3 inputs, 17 inputs, any number you want. And it behaves like what we've already talked about. So there's not too many surprises. All right, so let's say we know how scalar products work. In other words, we know the gradient. That's 1 down, but that still leaves us with at least 2 to go. So next one, let's go to, is the dot product. The dot product. Well, what is that? So for the dot product, we're going to call that divergence. And sometimes it's abbreviated as div. So you might hear div f. It's the divergence of f. So let's think about what the dot product does. So the dot product says you take the dot product of 2 vectors and you produce a number. Now for us, a number means a function which produces a number at the end. And so of all the various operators we're going to talk about today, the dot product is probably the most fun because it's oftentimes the easiest to do. So suppose our function is m and p. It doesn't have to be a 3-dimensional thing. And then when I write m and p, by the way, what I'm really doing is I'm saving a little bit of shorthand. So m is really a function of x, y, and z,
and n is a function of x, y, and z, and p is a function of x, y, and z. So these are multivariable functions. So the divergence of f is del dot f. So remember del, it's our partial derivatives. F is MNP. And so the way that dot product works is you multiply the entries together and add the result. So multiply the first pair of entries. Partial x of m, partial x. Second entries, partial y of n, partial y. Last, partial z of p, partial z. And you add it up. And the important thing is, this is not a vector. This is a scalar function. In other words, no vector here. All right. Now, you might say, okay, sure we can do it, but why do we want to do it? In some sense, we're going to see why a couple of sessions down the road, because we're going to get some beautiful theorems. But here's a rough idea of what's happening. When we're talking about divergence, what's happening is we want to say, what's happening at a particular point? So when I talk about the divergence of f at a point, what that measures is local contraction or expansion. So in particular, what we have is really you should think of when the divergence is positive, well, that means that it's expanding. So it's like source of flow. Things are coming out of it. When it's less than 0, you should think of it as it's contracting or compressing. Things are pushing into it. So you might call this a source, you might call this a sink. And when it equals 0, things are balancing out just right. So that's in sort of a very, very rough idea of what divergence gives us. And I will say this now and I'll say it again. There's some really beautiful online videos with amazing animation from people who have a budget, and I hope you seek those out because they give you a lot of insight. So let's do some examples. All right, find the divergence of the following. So, well, we get to make up some functions. So I can talk about f of x, y, and we'll just make up something, x squared plus e to the y, and of course, this has to be a vector valued function, so I've got to make it capital F. That's my first entry. Okay, second entry. Well, we'll have 2xy cubed. There we go. So, what's the divergence? Well, the divergence of f will be, we take the derivative of the first entry with respect to x, which is 2x, add to that the derivative of the second entry with respect to y, which will be 6xy squared. And there you go. That's the divergence. Okay, cool, awesome. Now, you might say for a second, hey, wait a second, you forgot something. What happened to this e to the y? Where did it go? And the answer is, it disappeared because when we take the entry, in the first entry, we're taking the derivative with respect to x, and e to the y is a constant with respect to x. And now you're probably thinking, whoa, so can you come up with a crazy function with an easy divergence? And the answer is yes. In fact, that's one of the hobbies that we do when we write final exams. We say, let's come up with a really crazy looking function. And they're just going to be like, ah! But then they take it and like, oh, yeah, that's a nice divergence. So suppose we say g of x, y, z. So what do we want? Well, the first entry, we're going to take derivative with respect to x. So maybe we'll put like a 3x. And then we can put some really crazy thing that only involves y, or only involves z, or maybe involves both. So like that. And then go to the second entry. That's derivative with respect to y. So I can put in a 4y plus 137. Go to the last entry. We take derivative with respect to z. And so we can put in something crazy like x plus 2 to the y minus 1 plus z. And then we say, okay, what's the divergence of g? Del dot g. Well, in the first entry, take the derivative with respect to x, you get 3. Second entry, derivative with respect to y, you get 4. Last entry, that's a 2, and that's not a z. I know my 2's and z's look similar. So see, my z has a little dash. Derivative with respect to z, it's a 1, giving us an 8. So you should be suspicious. If you see something that looks really terrible, then you should say, hey, I think that there's a tool to be used, and that tool should simplify. What's really happening here, and this will make a lot more sense later on, is that in some sense, if I were starting here and going backwards, I say, all right, well, the first thing is I get some function with x, and then something which is constant relative to x. So what I'm doing is I'm just choosing really, really weird-looking constants. So like 137, well, sure, that's a constant number. But this, y to the 17th arctangent z squared, is also a constant as far as x is concerned. So that's what's happening when we come up with examples like this. All right. Well, 2 down, 1 to go. And the last one, of course, was the cross product. And that produces something which we call the curl. So here's the thing about the cross product. You've got to remember this one fact about cross product. When we're dealing with cross products, it has to, absolutely 100% has to, be in 3D. You can't do a 2-dimensional cross product. You can't do a 4-dimensional cross product. You have to do a 3-dimensional cross product. Now, very conveniently for us, we live in a 3-dimensional universe, at least we think it is, and so it turns out, hey, it might have some good applications. So that's good news for us. So here we go. We have our vector-valued function as before because the cross product deals with vectors. But at the end, what we're going to end up with is a new vector-valued function. So how does it work? Well, this curl is del cross f. All right, no big surprises. We have the del, partial partial x, partial partial y, partial, excuse me, partial partial z, cross m and p. And now we get to one of the most, I think, either unusual or beautiful, depends on what day of the week I'm thinking about it, things in math, which is, this is how we usually compute the curl. Because that's how we think about taking a cross product. What do? Well, notice the first row, this corresponds to vectors. All right, it's I, j, and k. We've done that before. The second row comes from the entries in the first vector. Well, notice what are our entries? They're partial derivatives. So these are operators. The last row comes from the second vector, and what these are functions. And really, we could say they're multivariable functions. So we're taking this determinant of this matrix, which consists of vectors and operators and multivariable functions, and out comes something, and the really amazing thing is that we get something out that we can say makes sense, but even more amazing than that it makes sense is we're going to see that it's really useful. There's a beautiful result coming. Now, what is curl doing? Well, one way to talk about curl is you can say that what's happening is it's saying how much is your fluid rotating. So divergence was something about expansion contraction. So curl is something about how much is there deformation going on, whatever that might mean. All right, so there's a couple of notes that we should make here. This form, this is another way to talk about the curl of f, and very rarely do we memorize it because it's not easy to remember these things because there's a lot of partial derivatives and which one subtracts from which other one, and it gets tricky. It's really, this one is the one you should memorize. But you can see how you get from one to the other. So for example, suppose I was looking for what goes with the I direction, the first entry. Well, if you went down this way, you would see there's a partial y of p, which gives you partial p partial y, or p sub y. Now the other thing that will happen with I is when you go up starting at n. So it's n and partial z. So this will be the derivative of n with respect to z, or n sub z, and because we're going up in that direction, we subtract. And if you repeat that for all three of the entries, that's what you'll end up getting. Now there's going to come a moment sometime, a few sessions from now, when I'll say, have we seen this before? It looks familiar. Did we see this somewhere? And in particular, I'm going to point to something that looks like this. And you're going to say, oh, I remember that. That came from like the kernel. Like, oh, that's very interesting. So don't forget. Don't forget. It's a couple sessions from now that we're going to do that. And so don't forget. Don't forget. Okay, so let's do some examples. Find the curl for the following. Now, let's come up with a function. Now remember, it has to be something which is a three-dimensional vector-valued function. So the other thing is, curl is a lot harder to compute, so we're not going to get too exotic. So let's come up with a function that's not too hard to work with. So let's see. Let's do e to the x plus yz, comma, and then we have the next term. Well, let's just do x squared plus 2z cubed, and we'll come to the last term, x, y. So curl of f, curl of f, del cross f. So I'm going to use my box here. Got to give myself enough space because it's a big, lots of stuff to write down. I, j, k, partial x, partial y, partial z. Now the first entry, e to the x plus y times z, x squared plus 2 times c cubed, and x times y. All right, so far so good. So now we work it through. So we're going to take I partial y of x times y. So derivative of x times y with respect to y will give us x. Oops, I'll just write that as x. That's in the I direction. Now, next term, j partial z of e to the x plus yz. So I'm taking the derivative of e to the x plus yz with respect to z. And what do we get? Is we get y. So y times j. Then we have k partial x of x squared plus 2z cubed. So what's the derivative of x squared plus 2z cubed with respect to x? And the answer is 2x. So it'll be 2x, and that's in the k direction. All right? So there we go. That's good. Now that's going down. Let's go up. So here we have, well, e to the x plus yz partial y k. So if I take the derivative of e to the x plus yz with respect to y, we get z. And that's in the k direction. And finally, because we went up, it's subtracted. So subtract z times k. Partial z, x squared plus 2z cubed, and I. So we're going to take the derivative of this with respect to z. What will we get? Well, we'll get 6z squared. It's in the I direction, and because we went up, we subtract. So subtract 6z squared times I. And finally, we're going to take xy, partial x in the j direction. Well, take the derivative with respect to x of x times y. What do we get? Well, we get y. And it's in the j direction, and so we're going to subtract. And we're going to subtract yj. So what do we end up with? Well, we get x minus 6z squared in the I direction. The j terms cancel out. Now that's not so obvious that should happen. It's kind of beautiful, actually. What are the odds? Well, not 0, because they happen. And then the last term we get is 2x minus z. All right, well, there you go. I mean, is it right? Hopefully, maybe. We'll talk about a check later on. Now, you might at this point think to yourself, okay, what happened to the e to the x term? Well, notice there was no e to the x ended up here. Now, why is that? Well, where was the e to the x at? It was in the first entry, which was the m. And if you look down here where the m shows up, it only takes the derivative with respect to z and with respect to y. It doesn't take the derivative with respect to x. So it turns out that you can again make some functions look terrible by adding really crazy stuff. So I can, of course, come up with now really bizarre functions. So if I say g equals, say, stuff with x and stuff with y and stuff with z, if that's my g, then it turns out that the curl of g is going to be the 0. 0, 0, 0. Because what happens is, every time I take a derivative here, it's the derivative with either y or z, so I get 0. There, the derivative is either x or z, so I get 0. And there, the derivative is either x or y, so I get 0. So it is possible to sort of cook the books to get really unpleasant-looking expressions where the curl becomes nice. So this is something else to be aware of. So in general, you should think, have they tried to do something so that the answer is looking rather peculiar? Well, yes. Yes, we did. Okay, all right. Well, at least we admit to it. That's a good sign. At least we admit to it. All right. Now, let's put this aside for a second, because we're going to come back here and talk about a check you can do. All right, so let's find the following. So we want to find the curl of the gradient of f and the divergence of curl of f. So let's go through and talk about what happens. We're going to start with the gradient. So the gradient does what? You start with a scalar function, and out comes a vector function. Now the curl says, hey, let's start with the vector function, and out comes a vector function. And the divergence says, hey, let's start with a vector function, and out comes a scalar function. So we have these three things going on. So when we talk about the gradient followed by a curl, so that makes sense, because a gradient goes from a scalar to a vector, and curl goes from vector to a vector. So in particular, of course, because we're going to end up with doing a curl, we need to make sure this is a three-dimensional object. So we're going to start with f of x, y, z. Okay, so that's this part right here. So we have that the curl of gradient f, that's equal to the curl. Now, when I take the gradient, that's the vector of partial derivatives. So I'm going to use subscripts. F sub x, f sub y, and f sub z. So, what is that? Well, I, j, k, partial x, partial y, partial z, of f sub x, f sub y, f sub z. So this last row, that's what the curl is coming from. The middle row is the partial derivatives. First row is your vectors I, j, k. So, what do we get? Partial y with respect to f, z. So that's f, z, y, and that's in the I direction. Then partial z of f sub x, so that is f, x, z, that's in the j direction. And then k, partial x of fy, so that would be partial x of fy, that's f, y, x in the k direction. All right? Down, down, down. Now, other direction, going up. So we're taking partial y of f sub x. And that's going to be subtracted. F of xy in the k direction. Fy partial z of I. So that's fyz in the I direction. But because we went up, we subtract. And the final one, fz partial x, that's fzx in the j direction. So we subtract. And now we look at this and say, oh, wait a second. You see, order doesn't matter when we're dealing with nice functions. So let's assume we're a nice function. Those terms go away. Those terms go away. Those terms go away. And what we're left with is 0, 0, 0. So that when we do a gradient and then automatically apply a curl, the outcome is 0, 0, 0. Well, that's kind of interesting. It's very interesting, really. All right. Well, how about the divergence of the curl? Well, for that one, we have to sort of remind ourselves, what is the curl of f? Now, I happen to have a very convenient cheat sheet available for me to use, in that I found the curl of f. So I'm going to copy that down right there. So that's finding the divergence of p sub y minus n sub z, comma, m sub z minus p sub x, comma, n sub x minus m sub y. All right, so that's the divergence of that. Well, okay, so what do? Well, we take the derivative of the first entry with respect to x. So that'll be pyx minus nzx. Take the derivative of the second entry with respect to y. mzy minus pxy. Take the derivative of the last entry with respect to z. nxz minus myz. Now, well, it's a lot to hope for, but maybe pyx minus pxy. Cancel. nzx and xz. Cancel. mzy, myz. Cancel. And so what we're left with is 0 again. So somehow, when we do curl gradient or div of curl, we get 0. Now, this is actually a beautiful mathematical tool. And it's a very nice fact. Very nice fact. Now, how can we use it? Well, remember, I said, how do we know if our curl is right? Well, one way to check if your curl is right, just check the divergence. It's always got to be 0. Let's check that here. So take the derivative with respect to x, you get 1. Derivative with respect to y, 0. Derivative with respect to negative z, 2x minus z, negative 1. 1 plus 0 minus 1 is 0. So that's a good check. Probably a sign we did it right. So that's always good to know. Well, we're going to do a lot more with div and curl, and we're going to see some really amazing, beautiful theorems that involve these ideas. And so this is it. The last part of the class, vector calculus. It's going to be a lot of fun. So see you next time. Bye.